It's not make sense.
Negative 1/2, right?
Yeah, negative 1/2, but I cannot have log as negatives. What the heck is happening here?
Probably your
That's
upper
your,
bound.
yeah, it's your pi is 3.
Yeah, your upper bound is, you just make it like,
That's the boundary you put.
I'll copy this from the online questions.
pi over, make it pi over 6 and it will.
Yeah, pi over 6 will definitely work.
Sorry.
I don't think this is going to make sense. I'm sorry, I messed up this upper bound here. So let's make it pi over 6. That would definitely work.
So do this on the test. If it doesn't work, just.
So next thing about this double integrals is this endpoint doesn't really come up until the very last step. You can do all the things, right? So it's going to be 3. So it's going to be pi divided by 3. So cosine pi divided by 3, I know this is going to be 1/2, right? Log of 1/2 are now much more heavier. So it's going to be minus 3 divided by 2 log of cosine pi divided by 3 is just 1/2. Am I right?
Mm-hmm.
So now I have minus 3 divided by 2. Log 1 divided by 2 is just minus log 2, right? So multiply by minus log 2. So I'm having 3 divided by 2 log 2. Okay? So that's the final answer we have. Okay, questions? So the whole principle is still applying here. It's just one of the endpoints is not very friendly to work with in the very beginning. Okay, I have only one final remark I want to make before we move on. You remember, when we have the single variable integration, we have this explanation of a signed area. Do you still remember that? So if I have a function, this is f of x, integrating from a to b. So the integral from a to b, this function is talking about the area under the curve, right? So this is from a to b. So this area is actually from a to b fx dx. And also, if the curve is below x-axis, we're supposed to count the area as a negative. So it's essentially a signed area. Signed area. So a single variable integration is talking about signed area. A double integral is talking about signed volume. Okay? It is talking about signed volume, which is the volume above xy plane on this region below the curve, below the surface defined by this function. So if you have a surface, and then you can bound a solid below the surface above xy plane, restricted to this region apart. Okay, so we can also talk about the volume, the signed volume of this solid defined by this function. So this integral is nothing but the signed volume of that thing. So I can indeed make one simple observation here. In the end, I can easily check this is in the right direction. This is all positive. All right? These are all positive. This function is indeed positive within this region. So this is definitely making sense, right? So if you have a positive function, you take the integral, in the end you're getting a negative number. There is something wrong in your computation. We will elaborate on this signed volume again in the future. Okay, just I want to have you some preliminary idea about this double integral. So now I want to recall chapter 13 in the first term. Okay. So if you have any question about double integrals, then you can ask me after class. So in chapter 13, all we did is to take partial derivatives and also see what they're telling us. Okay. But in the very beginning, in chapter 13.1, we computed or we graphed several different two-dimensional objects, plane and also quadratic surfaces, So the planes are the easiest objects in R3, right? So in R3, the planes are the two-dimensional objects, or the function has to be linear and it is going to be a plane, right? If the function you have is a linear function. It's definitely a plane. And you have two-dimensional object. And in order to determine the plane, we need a normal line and a point. Okay, we need a normal line and a point. So if the normal line is equal to A, B, C, and point is equal to x0, y0, and z0, so the equation looks like A x minus x0 plus y b minus b multiplied by minus 0 of c z minus z0. So if you have taken this calculus sequence for several semesters, it should be pretty clear about the question you will be looking like. I'm not going to give you a question. Here is the normal line. Here's the point. Give me the equation. Right? So these questions are too straightforward. So usually I can give you a question. For instance, what is the plane that passes through 3 different points? Right? So we have got this kind of questions before. So the plane passes through 3 points. So think about how do you solve these kind of questions. You still have to end up with one vector and a point. You already have a point out of the 3, so you need to find the normal. So the normal vector is going to be a cross product between 2 vectors you find from these 3 points. All right, so we have done this in the very beginning. So you have 2 vectors coming from lining 2 different points. And then you do the cross product, you're going to get normal. And then you can choose any given point in these 3 in order to use this formula right here. Okay? So in terms of the quadratic surfaces, we introduced how many are there? So we have ellipsoid, we have elliptic paraboloid, we have a paraboloid with 1 shape, we have hyperbolic with 2 shapes, we have elliptic cone, and we have a hyperbolic paraboloid with a set of points. So in order to do this, the universal way of getting this is finding the intercepts and also finding the traces. Okay, so I will give you a function. Okay, I will give you a function. You need to come up with all the x, y, z intercepts if they are any, and x, y, z, and x traces if there are any. And then you need to identify this quadratic surface as one of the 6 different types, and then graph the surface. Okay, you need to graph the surface. I have distributed the points pretty nicely that it is not completely determined by how nicely your picture looks like. Okay? Finding the x, y, z intercepts will worth some points. Finding the traces will also worth some points. Identify which one it is will also worth some points. So you don't have to be too worried about your drawing skill. Okay? But still, listen to me carefully. Last semester we have this problem again. And because in the end we have different graders to grade all the Calc 3 courses, the one who grade this problem is very harsh. As long as the picture does not look like a paraboloid, for instance, you don't get any point. So you still want to practice your drawing skill. At least that you should be able to convince people this is one of the 6. Okay, so they have very different criteria. They look quite differently, right? So you should be able to at least draw them such that it is identifiable. Okay? So this is one of the questions as well. And then we move forward to talk about domain and limits of a function involving 2 independent variables. So I think this is probably chapter section 13.3, but don't worry about the sections. Okay? So domain and limits. So basically, I will give you a function f x y. Okay, so I want you to be able to find the natural domain. So in order to find a natural domain, you need to gather all the restrictions coming from square root, coming from log, coming from rational, coming from sometimes arc functions, but not too much, and so on. So there are natural restrictions coming from taking square root, log restriction of the denominator, and so on. Okay, and then you need to translate these inequalities into restrictions on x and y. Right? So this is what we did. And we also talked about the limit of the functions. And remember, taking the limit, there is one easy case and one slightly more challenged case. If I'm taking the limit of a function where the point is indeed in the domain, okay? So for instance, if AB is in the domain, the limit xy goes to AB, fxy is nothing but f of AB, all right? So if I'm computing the limit of a function when xy approaches a point, if this point is already in the domain, you don't have to worry about that. Just plug in numbers, and that's all, right? For instance, I can give you a question looking like log sort of xy, where xy approaches e squared and 9. Okay? So if xy approaches e squared and 9, I look at this point, e squared and 9, plug in here, square root, okay, log, still okay, so I'm not gonna be worried about it at all, but plug in e squared and 9 into this equation. You just evaluate a log function, and that's all. All right? So this is the easiest case. The other case is to prove the limit does not exist. In order to prove the limit does not exist, you need to come up with two different passes for xy to approach this fixed base point, such that these two passes will give you two different limits. All right? So the most frequent point we see is so-called the origin, 0, 0. So for instance, if I have a function x divided by square root of x squared plus y squared, limit xy approaches 0, 0. I want to prove this limit does not exist. I need to come up with two passes for xy to approach to 0, 0. And this fraction will end up with two different values, all right? So the popular choices for your passes, especially if the base point is the origin, are t0, where t goes to 0. So this is approaching the origin from x-axis. And then from 0, t goes to 0. This is approaching 0, 0 from y-axis. And we also talked about this straight line t, kt, where k is a fixed number. This one is approaching the origin from a straight line with slope k. Okay, so you can approach your origin by any slope of a straight line. Okay, a straight line with arbitrary slope, you can use k to be 1, 2, 3, 4, or whatever. Usually, 2x in the y direction will be sufficient. If they're not, go for these straight lines. Okay, as long as you can end up with two different answers, you're good. Okay, you can prove the limit does not exist. And then we actually computed the partial derivatives and learned a lot from the partial derivatives. So computing the partial derivatives is really easy. The problem is how much we can tell from these partial derivatives. So one thing we can do is to gather them together into a directional derivative. All right? So if I have a function fxy, I can compute fx, compute f of y, and this is going to be the partial derivative with respect to x, with respect to y. And we discussed this a lot about what they mean in terms of rate of change, in terms of slope of a tangent line. If you still remember, you have a curve parallel to x-axis. The slope of the tangent line to that curve is fx. You have a curve on the surface parallel to y-axis. You have a slope of a tangent line. This is what the fy is talking about, right? And also, we can gather them together and rename it as a gradient vector. Okay, so this is a gradient vector. And also, we can use this gradient vector to compute the directional derivative for any given directional vector. So this is gradient vector multiplied by u, where u is a directional vector which has to be unit. So this is going to be the rate of change if you move the independent variables in the direction of u. If I'm giving you a vector which is not of unit length, you need to normalize this in the very beginning in order to even use this formula. In this formula is a dot product between the gradient vector and the directional vector. Both of them are vectors, right? And also from this formula, we quickly determined u max and u min. So there are two values of the rate of change. U max is where you can achieve the maximum rate of change. And this is equal to length of the gradient, and the minimum rate of change is minus length of the gradient. All right? And also we can easily determine max and minimum direction. So the max direction is given by gradient of f divided by its length. Minimum is minus the direction, the opposite direction of the maximum. Okay, so these are the formulas involving the partial derivatives. Okay, so you should be able to very nicely compute all those things. And remember the difference between these values. The rate of change as the directional derivative has to be numbers. Okay, gradient and directions are all vectors. And we also discussed the relation between these two vectors with the level curves. All right? You still remember the relation between these two vectors with the level curves. So if I have a function f x y, I can compute the level curves at level is equal to 0, 1, and 4, and so on. All right? So you can draw the curve on the xy plane. So this is 1, 2, 3 different curves. Just one simple example. Okay? Of course, it depends on what the formula you get for the function. Okay? You get a formula, and then by plugging the levels, you're supposed to get a family of curves. These are the level curves. And we learn about the relation between these vectors with the level curves. All right? The gradient has to be orthogonal to the level curves. In particular, because these two are both in the direction of the gradient vectors, these two vectors are both orthogonal to the level curves. Am I right? In particular, if, say, this is k equals 0, k equals 1, k equals 4, this vector is pointing to the increasing direction. Which means if I'm looking at u max at this given point, it has to be orthogonal to the level curve and